Hello class, Dr. Barnes here. Let's talk about the Z transform. Okay, so Z transform. So Z transform is very similar to the Fourier transform and then the Laplace transform. But Fourier transform and Laplace transform are used for continuous time signals. Okay, to analyze continuous time signal. But Z transforms are used for discrete time signals. Okay, so to analyze discrete time signals. So what are discrete time signals? Okay, so now we I know you'll be familiar with a signal. This is a signal. Okay, here is what x x of what t. Okay, x of t, and here is what t. Here is 0. This signal is called what? Continuous time signal. Okay, so from this signal also I can realize another signal from this particular one by taking samples of this one. Okay, let's say, okay, so you can see that this signal is what? Very what? Similar to the one I have above. Okay, but here is what? Discrete. You can see that the points are occurring at what? Specific instances of time, but here it's continuous with time, but here specific instance of time. Because I'm taking what? Specific instance of time, the points are discrete, and then I'm taking samples. I'll call it what? Number of samples I took, so I'll call it n, and here I'll call it x of what? N. Okay, so this is a continuous time signal. This what? Discrete what? Time what? Signal. Okay, continuous time what? Signal. This is what? Discrete time what? Signal. Okay, so Z transforms are used for what? Analyzing discrete time what? Signals. Okay, for analyzing discrete time signals. So now, so what they actually do to the discrete time signal is that converts it to the frequency domain. Okay, to the frequency what? Domain. Okay, so it will convert a discrete time signal to the frequency domain, and it normally uses this particular formula. So x of what? Z. Okay, x of z is, which is the Z transform of what? X. The Z transform of x is equals to summation, okay, infinity, n is equals to minus what? Infinity. X of what? N, and then to what? Z of minus what? N. So this z minus n is a complex variable. Okay, so this z minus n is a complex variable, which is equals to what? R into E, okay, R into E into what? J omega. See, this omega here is the frequency what? Component. And R here is the radius of the circle. Radius of the circle. Okay, so now basically this is how it operates. This formula is called two-sided Z transform. This is called two-sided what? Z transform. We also have the one-sided what? One-sided Z what? Transform, which is equal to summation up to infinity. N is equals to what? 0. X of what? N. Okay, into x of z of minus n. So it is the what? This one is called what? So this one is also called one-sided. Okay, one-sided Z transform. Okay, so the difference is that here it's starting from negative infinity to infinity, but here 0 to what? Infinity. Okay, so those are the two that we have there. Okay, then from there, you see that in the normally after converting a signal to the frequency domain, we should be able to turn it back to the what? To the original signal. So after converting it from what? X of what? Z. After converting this X of what? N, discrete time signal into its frequency domain. Okay, here Z what? Transform, which is what? X of what? Z. Okay, we should be able to turn it back to what? X of n. In that case, we use the what? Inverse Fourier what? Transform. So the inverse Fourier transform will take what? X of what? Z. Okay, and then it's not inverse Fourier transform. Inverse Z transform. Inverse Z transform. So it will convert it to what? X of what? N. And the formula for the inverse Z transform is actually like this. Okay, so the formula for the inverse Z transform. So you're going to have X of what? N is equals to what? X of N is equals to what? 1 over 2 pi what? J. Okay, into this particular integral C. Okay, Z of minus N. Okay, into X of what? Z d what? Dz. And this one is for what? Inverse Z transform. Okay, normally this is used for reconstructing the signal back to its original form. Okay, all right. So now, one particular important thing that we have to know with respect to Z transform is the region of what? Convergence. Okay, is the region of what? Convergence. Okay, so briefly, let's see what this region of convergence actually is like. Okay, so we have the region. This is just like Laplace transform, region of what? Convergence. Convergence. Okay, region of convergence, ROC. Okay, so basically it is the range. It is the range of values. Okay, okay, the range of values of Z. Okay, for which the summation what? Converges. Okay, converges. All right, and then which summation are we talking about right now? We're just talking about the Z transform what? Summation. Okay, Z transform summation, which is equals to this. Okay, n is equals to minus infinity. Okay, x of what? N into what? Z minus 1. So the range of values of Z for which this summation would converge is called the region of what? Convergence. Okay, it's called the region of convergence. Okay, so getting to this point, let's just take one brief example. Let's take one brief example and see how it works. So let's say that we have a discrete time sequence x of n, which is equals to 1, 2, 3. Okay, 1, 2, 3, and 2. Okay, let's say these are x of n. Okay, and then let's say that we want to find a Z transform for this particular sequence. Okay, this particular sequence. Okay, so now to find a Z transform for this particular sequence, all right, what we shall do is that let's put down the general formula. Okay, so Z transform, okay, of x of what? N. Okay, Z transform of x of n, which is the same thing as what? X of what? Z. Okay, for this one is actually equals to what? N equals to here, let's put down the general formula, minus infinity to what? To infinity. X of what? N to Z minus what? N. Okay, so this is the general formula. So now here, x of what? Z is equals to, what are we starting from? Right now here, we can see that we are starting from what? 0. Let's say that our arrow is actually on this one. Okay, our arrow is on this one. So we're starting from n is equals to 0 to what? To 4, because, no, if here is 0, then here is 1, here is 2, here is what? 3. So 0 to what? 3. Okay, so now here x of n. What is the x of n that we have here? Okay, we can just put them together. 1, 2, 3, 4. Okay, so this, let's say this our x of what? N minus what? This one. Okay, so let's say that we can do it this way. So now here, okay, so now here, our x of what? Z is actually equals to, our x of z actually will be equals to the summation, what we have to do. So basically, this thing I have written here is the same thing as saying that n is equals to what? 0. And then here is 3. Here is x of what? N. Here is z minus what? N. Okay, so the z of n, the x of n, that is what I put the sequence over there. Okay, so it's the same thing as this. Okay, so now here, moving on from what I have here, what I can say is that, let me just expand this particular formula that I have. Okay, if I'm expanding this one, then I'm going to have x of what? 0. So I'm going to have what? X of what? 0. Z exponent minus 0, z exponent minus 0 will not be important, so I don't have to put that one. Okay, so here plus what? X of what? 1. Okay, plus what? X of what? 1. And then z of minus what? 1. And then here I have plus what? X of what? 2. Z of z, okay? Z of minus what? 2. Plus x of what? 1, 2, what? 3. Z of minus what? 3. Okay, so that's what I'll have. So what is x of 0? X of 0 is what? 1. Plus, what is this place? Z minus what? 1. But basically, what is the number here? Is 2. Okay, so let me put 2 here. Okay, then plus this place. What is the number here? Is 3. So let me put 3 here. Z of minus what? 2. Plus this place. What's the number there? Sorry. Here is 2. Is 2. Alright, I'm sorry. It's 2. Here is 2. Okay, it's 2. Okay, so let's see. Plus what? 2. Z of minus what? 3. Okay, so basically that is what, this is how you can do it. Okay, so now basically I'll have 1 plus 2. Okay, 1 plus 2 over what? Z, because you can write this one, you can write it this way. Okay, so this one you can write it this way, plus 3 over what? Z squared, plus 2 over what? Z what? Cube. So how do you do this one? Okay, so now what you can see is that if you divide this Z, okay, if you divide this Z by 0, this is going to be infinity. If you divide this Z by this 3, sorry, if you divide this 2 by 0, it will be infinity. If you divide this 3 by 0, it will be infinity. If you divide this 2 by 0, it will also be what? Infinity. Okay, so now what is our ROC? But mind you, we can say that it actually goes on and on and on. Okay, I have to put it there, that it goes on and on and on. Okay, so now it goes on and on and on. So plus on and on and on, it goes on. So this is my x of what? Z. But I have to find my ROC. So now my ROC is when the summation will converge. But if I divide this 2 by 0, I'll get infinity. 3 by 0, I'll get infinity. 2 by 0, I'll get what? Infinity. Okay, but always the ROC, okay, is such that the summation from infinity, n is equals to what? Minus what? Infinity. Okay, x of what? N into z of what? Minus n should be less than what? Infinity. So that means that I cannot what? Take what? Infinity. I cannot take infinity. Okay, so now then the summation, what I can write is that when I divide here by 0, infinity. If I divide 3 by 0, infinity. 2 by 0, infinity. So the ROC, okay, so ROC, okay, is the entire z plane, okay, except what? Z equals what? 0. Because when you divide it by 0, you get what? Infinity. Alright, so that's how you can just do this one. See you in the next class.